We have already studied several types of convergences, some theorems related to them, and also the interrelationships among them. As for example, it is clear that if xn is a sequence of random variables that converges in L1, that is, that converges to x, another random variable in L1 or LP, that means pth mean, then it can be easily shown that this xn converges to x in probability, just by a simple application of Markov inequality. But the question is, can we say that if a sequence converges to a random variable x in probability or maybe in distribution, can we say that this will converge to x in L1? So this is a very important question, because although the other types of convergence gives us the behavior of the distribution of a sequence of random variables in terms of the distribution of the limiting random variable, but what about the expectation? Can we straightway say that the expectation of the sequence of random variables will also converge to its expectation? Now, to study these interrelations or this behavior, we need to introduce another very important concept in probability theory or in measure theoretic probability theory, which is known as uniform integrability. So today we are going to introduce the concept of uniform integrability, and we will discuss a few very elementary results that will be extremely important in our further study. First, we will define a sequence of random variables which are uniformly integrable. So let us start with a sequence xn in greater than equals to 1, a sequence of random variables on a probability space omega, script b and p. As we know that omega is the whole space and script b is the sigma field generated by the class of subsets of omega, and p is a probability measure defined on this omega and script b. So on this we define a sequence of random variables xn. Now the formal definition of uniform integrability goes like this. This sequence xn in greater than equals to 1 is said to be uniformly integrable, or abbreviated as ui, if for every epsilon is greater than 0, that means very small positive quantity, there always exists another small quantity, that is delta, which is greater than 0, that means a very small positive quantity delta, such that supremum over n of the integral over a mod xn dp less than epsilon, whenever probability of the set on which the integral is taken, that is a, or probability of a is less than delta, and supremum n greater than equals to 1, supremum of expectation of mod xn less than equals to c less than infinity. So this is the definition of uniform integrability of a sequence. Now if we look at this definition very carefully, we can find some analogous concept we have studied in real analysis. So from real analysis we know that if fx is an integrable function on x, script b and mu is any measure defined on this measurable space x and script b, then integration fx d mu x or integration over a less than epsilon if mu of a less than delta. Now we know that this is known as absolute continuity of integral. So if we look at the definition of uniform integrability and the definition and this integrability from real integrability of a function with respect to a measure mu from the real analysis class, we see that we can immediately say that uniform integrability of random variables in a sense is a uniform absolute continuity. So this is a nice analog between real analysis and this concept that we are now going to, we have just introduced, the concept of uniform integrability on a probability space of a sequence of random variables defined on a probability space. Now we will discuss one equivalent relation of uniform integrability, because sometimes it is not very easy to check the condition of uniform integrability according to the definition. So we explore an equivalent relation of uniform integrability here in this theorem. Here xn be a sequence of random variables, then xn is uniformly integrable if and only if limit b goes to 0, integration over mod xn greater than equals to b of mod xn dp equals to 0 uniformly in n. That means whenever we say that xn is uniformly integrable, we are now stick to the definition of uniform integrable, and we will show that this definition holds if and only if this condition limit b goes to 0, integration of mod xn dp over mod xn greater than equals to b equals to 0 uniformly in n. So from now on, it is enough for a sequence of random variables to see whether this sequence is uniformly integrable or not. It is enough to check this condition, because this is both necessary and sufficient. This is the importance of this result or of this theorem. Now we are going to prove this theorem, both if part and as well as only if part. First, we will prove the only if part. That means we assume that the sequence xn n greater than equals to 1 is uniformly integrable. Then naturally, according to the definition, we can say that for every epsilon greater than 0, we can always find a delta which is again small but greater than 0, such that supremum over n integration over a of mod xn dp less than epsilon, we call this condition as 1 whenever probability of a less than delta and supremum over n greater than equals to 1, expectation of mod xn less than equals to c, which is less than infinity. Now this is the condition 2. So this comes from the definition of uniform integrability, or the way we defined it. Now it is clear that supremum over n greater than equals to 1, expectation of mod xn less than equals to c, immediately implies that expectation of mod xn less than equals to c for every n. Because since the supremum is less than equals to c bounded, then obviously the individual expectations must be bounded. So we just apply Markov's inequality, because you see this Markov inequality is again an extremely useful inequality in probability theory, and we have already seen its use in many applications in many theorems and results. So here also we use Markov's inequality to see that probability mod xn greater than equals to b less than equals to 1 by b into expectation of mod xn, which is less than equals to c by b. Now this c is finite, so c by b goes to 0 as b goes to infinity. That means, and this is uniformly in n. So what we get, that probability mod xn greater than equals to b goes to 0 as b goes to infinity. Now recall, if you recall the statement of the theorem, this mod xn greater than equals to b is the set on which we are going to consider an integral. Now from 1, we can always say that supremum over n greater than equals to n and integration mod xn over mod xn greater than equals to b modulus of xn dp is less than epsilon if b is large enough for a given epsilon greater than 0. The reason is the previous line, because probability of mod xn greater than equals to b goes to 0 or arbitrarily smaller than any arbitrarily small positive quantity. So this follows coupled with condition 1. So 1 and 2 immediately implies that limit b goes to infinity, integration mod xn greater than equals to b modulus of xn dp equals to 0 uniformly in n. So proof of one part is complete. So all we can show that if we use the formal definition of uniform integrability, we can show that this condition as stated by the result holds true. Now we will prove the converse part, that is if part. That means we assume that limit b goes to infinity, integration over mod xn greater than equals to b mod xn dp equals to 0 uniformly in n. For every epsilon greater than 0, we can have integration over mod xn greater than equals to b modulus of xn dp less than equals to epsilon. Because this condition that we have already assumed, because of we are going to prove if part, since this is uniformly in n, we can always find such an epsilon for b large enough. B is obviously great positive, and for every n greater than equals to 1 this holds. Now let us consider what happens to expectation of mod xn, because in the main definition of uniform integrability we have this expectation. So expectation of xn, we can split this expectation over two different sets. One is mod xn less than b, another is mod xn greater than equals to b. So we can immediately write integration over mod xn less than b mod xn dp plus integration over mod xn greater than equals to b mod xn dp, which is less than the first part. If we replace mod xn by b and replace the whole integral by 1, then first part is less than b, and the second part, by virtue of the condition that we have assumed and which we see immediately in the previous line, that the second part is less than epsilon for arbitrarily small epsilon. So we see that expectation of mod xn less than b plus epsilon, that means expectation exists. Now let us put delta equals to epsilon by b. Since delta is arbitrarily small and b is large enough for a fixed epsilon, we can always find a delta such that which is equals to epsilon by b. Then for a belonging to script b, there is a sigma field with probability of a less than delta, and noting one important thing, that a intersection modulus of xn greater than equals to b, this set is a subset of a. So integration over a mod xn dp equals to integration over a intersection mod xn less than b mod xn dp plus integration of mod xn dp over a intersection mod xn greater than equals to b. So we are just splitting the set A again exactly in the same way that we have already seen, and the first part is again less than b into probability of a, because if we replace mod xn by b, this will be less than b, and integration over a intersection mod xn less than b dp, we replace this by probability of a, because this set is a subset of a. And the second part we keep it, second part we are again changing this thing to modulus of xn greater than equals to b mod xn dp. So we are considering this integral over a bigger set. Now we know that probability of a is less than delta and delta equals to epsilon by b. So immediately we have this entire quantity is less than b into epsilon by b plus epsilon, which is equals to twice epsilon, and this is uniformly in n. So immediately we see that supremum over n integration of mod xn dp over a, where probability of a is less than delta, this is less than epsilon, where epsilon is arbitrarily small, and that naturally completes the proof. So we see that here we get an equivalent condition of uniform integrability, which is slightly different from the definition, but although follows from the definition and vice versa. But it is easy to check this condition rather than checking the conditions given in the formal definition of uniform integrability. Now we discuss two interesting results relating to uniform integrability of a random variable, and we will discuss its implication. Now just first note that integration mod x dp over modulus of x greater than b, we can write it as expectation of mod x into indicator function over mod x greater than b. So this is another way of writing expectation, or another way of writing integral in terms of expectation, which will be useful in the subsequent steps. First result we state as suppose x is a random variable such that expectation of mod x less than infinity, then expectation of mod x into indicator over mod x greater than b, this goes to 0 as b goes to infinity. Now this thing is intuitively very clear, because we are multiplying this modulus of x by an indicator function which depends on b, and as b goes to 0 we are going away, we are going towards infinity or minus infinity. So that means that almost the set on which we are considering this indicator function becomes extremely small or sometimes might be empty. So this is intuitively clear, but a formal proof is also very simple. Just see that 0, this modulus of x indicator over mod x greater than p is a non-negative function, non-negative quantity, and it is also monotonically increasing in b. Hence, using monotone convergence theorem, since we have have one variable which is monotonically increasing, we can easily use monotone convergence theorem. So naturally we have expectation of mod x, indicator of mod x less than equals to b, goes to expectation of x, because here you see we are taking this indicator over the complement of that of the set that is given in the result 1, that is modulus of x less than equals to b. So as b goes to infinity, we are trying to capture the entire support of the variable x. So basically when b goes to infinity, this approaches to just expectation of x, that is over the whole space. So it naturally converges to expectation of mod x as b goes to infinity. On the other hand, expectation of x, again we can split this expectation of mod x is nothing but the integral, we can write in terms of integral, and we can split this integral into two sets. One is mod x1 greater than b, another is mod x less than equals to b, and again writing back the integral in terms of expectation of a variable into the indicator function, we can get this thing as expectation of mod x is expectation of mod x into indicator over mod x greater than b plus expectation of mod x into indicator over mod x less than equals to b. And we know that expectation of mod x less than infinity, then naturally we have expectation of mod x indicator over mod x greater than b goes to 0, because as b goes to infinity, the second term, that is expectation of mod x into indicator over mod x less than equals to b, this goes to expectation of mod x, and this expectation of mod x cancels from left hand side and right hand side because expectation of mod x is less than infinity. That's why we can cancel it. So we are left with only expectation of mod x in the first term, expectation of mod x into indicator over mod x greater than b, which definitely goes to 0 as b goes to infinity. So this is again using the trick that we are splitting a set by one particular pattern, rather mod x greater than b and its complement, and then looking the behavior of the integral or the expectation at each of these sets. This proof is very simple. So we are again using the same technique that we have already used previously many times. Here we are using the same technique. Now result 1 indicates that finiteness of first order moment implies that the random variable is by itself uniformly integrable. So this is a very strong result and a very nice result, that whenever we have finite first order for a random variable, we can immediately say, without checking anything, just due to result 1, we can immediately say that the random variable itself is uniformly integrable. Thus we see that expectation and uniform integrability are somehow related, that as we have explained before. So the natural question is, can we extend and explore this relation between expectation and uniform integrability a little more? Yes, we can, and naturally to this end we can have another interesting result, which we call result 2. Result 2 is related with a sequence of uniformly integrable random variables, and if we have a such sequence, then we can immediately show that supremum over n of expectation of mod xn is less than infinity. That means if you consider expectation of mod xn and take supremum of that is again finite. The proof is very simple. In fact, this is again an application of the same technique that we have already used many times, that is splitting a particular set in terms of a particular part and its component and its complement actually. So the proof goes like this: since xn is uniformly integrable, we can always say that there exists a b where b is very large, such that supremum over expectation of xn into indicator of mod xn greater than b is less than equals to 1, because it is finite, so let us call it less than 1 without loss of generality. So thus for any n greater than equals to 1, expectation of mod xn equals to expectation of mod xn into I of mod xn greater than b plus expectation of mod xn into I of mod xn less than equals to b. And naturally this is less than equals to b plus 1, because in the second part we replace xn by b and just take the expectation of the indicator function, it will be again 1, so it will be b plus 1 and it is less than infinity. This second result ensures that uniform integrability implies boundedness of expectation of a random variable. So whenever we see that random variable is uniformly integrable, we can immediately say that the expectation of the random variable is bounded, which is a very important result or important notion in probability theory, and which will be used, which has immense application later on. Next result is also in the same line, but it has also a deep significance. Just recall that we can write integration mod x dp over mod x greater than b as expectation of mod x into I of mod x greater than b. Then result 3 states that suppose xn is a sequence of random variables and y is another random variable such that supremum over n mod xn less than equals to y and expectation of y less than infinity. This is very important, that first moment of y is less than finite. Then we can show that sequence of modulus of xn is also uniformly integrable. The proof is again using the same technique, that is, we immediately see that modulus of xn integration over mod xn greater than b is less than equals to y into indicator of modulus of y greater than b. So we are considering the variable over the set mod xn greater than b and mod y greater than b. That is why we are using indicator function on both sides. Therefore, for any n greater than equals to 1, if we take expectation of mod xn into indicator of mod xn greater than b is less than equals to expectation of y indicator of mod y greater than b, this goes to 0 as b goes to infinity, because expectation of y is less than finite, is less than infinity. That means finiteness of the first moment of y. So this proves the result 3. That means here we have, after discussing this after defining uniform integrability, we have considered these 3 results, and somehow they are related with the expectation and uniform integrability. So we have introduced the concept of uniform integrability and we have also given the formal definition of uniform integrability. That means when we can say that a sequence of random variables will be uniformly integrable, obviously with respect to a particular probability space. Now we have also seen a few more elementary results which deals with some kind of equivalent definition or equivalent relation between the formal definition of uniform integrability, because sometimes in some problems it is not very easy to check whether a particular sequence of random variables is uniformly integrable as per the formal definition of uniform integrability. Rather, it would be sometimes easy to check whether the equivalent relation of this uniform integrability. That means it is enough to check some conditions, and so that we can say immediately that the sequence is uniformly integrable. And these conditions have been explored through the results that we have already discussed, and we have already proved this result in detail. So now that we have a feeling of what is the meaning and what is the interpretation of uniform integrability, now we can move on to our further study to investigate the relation between, or how this uniform integrability plays an important role in exploring the convergence of different types of convergence of a sequence of random variables and its relation with the expectation, that means with its moments. We will discuss them in the future talks.